Hi everyone, this is the first video of a series about polymer reaction engineering. We will see why polymers are so versatile, and answering this question will bring us close to explore some of the characteristic features of polymers. This in turn will bring us closer to understanding what polymer reaction engineering is all about. Now, we don't know each other, but I'm pretty sure that you have slept on a mattress during your lifetime. You have drank some water from a bottle. I dare to guess also that you have some sports shoes and that you have worn some masks during the COVID epidemic. Now, all these items are in total or in part made of polymers. The same goes for car seats, some t-shirts, even paints or the coatings of wind turbines. Polymers are everywhere. There are countless other examples, but how can polymers have so many different applications, right? One might wonder. Or at least I hope you are, because now I'm trying to answer this question. Let's start from what they are. So polymers are macromolecules. They're very large molecules or chains consisting of several small molecules, and these are called monomers. Now, based on the definition, we can already sense, I think, the broad variety hiding behind the word polymer. How long are these polymer chains? All the same length? Are there different lengths? How many monomers do even belong to each chain? All of the same type, different ones? Which structures do they form? Let's depict monomers as spheres, as the ones that you see here on the screen, and build polymer chains to approach this variety. And we will start with one type of monomers only, and we'll start acknowledging that monomers will react with each other. We will see how in later videos, and they form chains of different lengths. So you could have a dimer, right, like 2 repeating units. You would have a trimer, 3 repeating units, and so on, up to a generic N-mer, so made out of N repeating units. Note that if a monomer is within a chain, it is called a repeating unit, whereas if it is still free, then it's simply called a monomer. Either way, we have said that polymers have a chain length distribution. There are, several chains of length 2, 3, 4, n. This chain length distribution might look like the one in the graphic. Important note, the chain length distribution of a polymer is crucial, since the polymer properties are determined by the entire chain length distribution. Now, just to make an example, viscosity and mechanical properties of a polymer, they strongly depend on the chain length distribution. So we can already understand that even if we were to use only one type of monomer, we can strongly affect its application properties, or the application properties of the polymer rather, if we are able somehow to regulate the chain length of the polymers, right, or the chain length distribution. So far, we have discussed the chain length, right? But what if we go back to our previous example where we have different types of monomers and not only one, right? In the first screen that we saw. And, well, sure, we can make homopolymers, right? So chains of different length made of the same monomers, but we could also use several or 2 comonomers and form copolymers. Okay, so polymer chains made of 2 types of monomers. And again, we have the possibility of having different lengths here, of course, as well. And the game, as you probably imagined by now, can continue with terpolymers using 3 types of monomers and so on. Now, why is this relevant? Well, some monomers give, as a result, very soft polymers, while others are related, let's say, or produce very rigid or stiff polymer chains. And if we mix the 2 types of monomers, we will get in-between results. That is why it's important for us to know that we can control the polymer properties by changing the number or the types of monomers, right? And it's not only the number of monomers, but also the way they arrange within a polymer chain. So let us keep looking just at copolymers. So we focus not on just on two types of spheres here, the yellow and the blue ones. Well, if we arrange the monomers randomly, one speaks of a random or statistical copolymer, right? If instead we are able somehow to place each comonomer close only to another one, meaning that each comonomer reacts only with the other comonomer, then we will have alternating copolymers. We could also have block copolymers. So we first polymerize one type of monomer and then the other. And again, we could have a graft copolymer. So we would have a backbone, right? In this case, the blue one. And then from there, a graft arm, so-called, would arise here, the yellow one. Now, the monomer sequence, if you will, extends the concept we saw before. Each monomer brings different physicochemical properties, and combining them in different sequences will also affect the polymer properties. So far, we saw how long the polymer chains were, which monomers, they are composed of, and the sequences within those polymers. But what did all the chains that I've showed you so far have in common? They were linear. And as you have guessed by now, also polymer architecture is a key feature. So we saw already these linear chains. Here we're using a third polymer, so with different 3 types of monomers, but we're depicting them as linear. But we could have also branched chains, for instance, with short branches that are either intentional or caused by a side reaction. What else could we have? Well, we could have long branches, right? Or we could even have cross-linked polymers, where the chains are really connected to one another. And these ones have very strong mechanical properties, especially when we compare them to just linear chains. Also, their capability of swelling, so increasing the volume of the polymer by soaking up a given liquid, like in diapers, for instance, is affected. So this capability of swelling is affected by cross-links. What else do we have? Well, we have star-shaped polymers, right? And still keep in mind, all of these shapes affect the final polymer properties. So far we have used spheres to represent free monomers and repeating units, but we do know that molecules can themselves, of course, organize in space. Now recall that stereoisomers are defined as having the same molecular formula and sequence of bonded atoms, but differing or differences in the geometric positioning of the atoms in space. So to describe this, we need to consider, well, bonds behind, bonds in front, and bonds in the screen plane, okay, as the ones depicted here on the right. Now, this molecule here, well, represents actually an isotactic macromolecule with identical configurational repeating units. Right here we call them R1 and R2. Okay, so this is an isotactic macromolecule. The tacticity actually impacts the physical properties. Okay, so again, the structure influences the degree to which a polymer has a rigid, crystalline long-range odor or flexible, amorphous long-range disorder. Here, now we see a syndiotactic polymer chain, so one that has alternating substituents along the chain. You see, R1 and R2 are not anymore all on one or the other side, but they really are alternating. We could also have so-called an atactic macromolecule. These polymers tend to be amorphous and flexible, whereas isotactic ones more crystalline and rigid. And tacticity is of particular relevance with so-called vinyl polymers. For instance, polypropylene. We will see this also in a later video. But so at the beginning of the video, we saw the variety of applications that polymers have. Thanks to the definition, polymers being chains made of monomers, we begin to appreciate how a class of material can be so diverse, because there are so many options to customize them and their resulting properties. Two polymers we saw may differ because of their chain length distribution, or the number or types, if you want, of monomers involved, right? Homopolymers versus copolymers. We also saw that the monomer sequence within the chain plays a role. The polymer architecture as well, linear chains, branch chains, and so on. And then finally, the tacticity. Now, what is the best thing about all of this? We can influence all of the above features, which are also called the microstructure of the polymer, during the reaction. Actually, for this reason, polymers are called products by process. So, in other words, if you want, polymer properties are determined during the reaction. and we try our best to steer the reaction in the desired direction. And if you will, this is what polymer reaction engineering is all about. We want to control the polymerization to achieve the desired polymer microstructure and properties. And we will see in the next videos of this series, which type of reactions are relevant in the different kinds of polymerization and how we can at least try to control these reactions to obtain the polymer properties we want, hopefully with an eye on safety and sustainability. Now, the challenge is that there are so many variables that affect the microstructure: temperature, additives, solvent. The list is really very, very long. The good thing is that this is a challenge we can take on because we have mathematical models on our side, mass and energy balances supported by experimental data. An example is this left-hand side of an equation, which I'm just showing here. You want to know what it means and how to solve it? More in the next videos. Now, to recap, what did we see? Well, polymers are versatile because behind the word polymer are actually very different macromolecules height, right? With different chain length, types and sequence of monomers, architectures, and tacticities. We have seen that the polymer properties are determined during the reaction, and PRE is all about controlling, or at least trying to control, the reaction to obtain the polymer that we want. Now, we will see how mathematical models can come to the rescue with experimental data, but this is for the next video. So in the meantime, thank you a lot for watching. If you like the video, have comments or questions, I would be happy to hear from you. See you next time.